So what is dark energy? That is the question. We don't really know what dark energy is. A lot of people say it's just a label for our ignorance. What we know about 100 years ago is Edwin Hubble showed that the universe is expanding, and that results from what we came to call the Big Bang explosion. Then in the late 90s, a group of astrophysicists went out to measure how much that expansion rate was slowing down due to gravity. The force of gravity between galaxies, pulling them closer together, would tend to slow that expansion down. And what they came up with was negative number. The expansion rate is actually accelerating, getting faster and faster as it goes along. And what causes that? Well, it has to be some kind of energy field in the universe, and we call that dark energy because it doesn't seem to give off light or interact with light in any way. But that's about all we know about it. We know that it's 70% of the energy density of the universe around us, but we don't know what it's made of. We don't know how it behaves. And it's really probably the most outstanding problem in physics right now and in our understanding of the universe. What is dark energy? It's not that difficult to get a wrong answer in an experimental science. There are lots of ways to make mistakes, but it's very unusual for two independent teams doing two independent sets of measurements to have the same mistakes in the same way, in the same amount, and get the same answer. That is not something that could easily happen. So that's what led people to think that it might be right. And since then, we have done a lot of confirmations with other kinds of measurements, all of which seem to show that yes, there is this mysterious dark energy, and we do live in an accelerating universe. The approach we're trying to take on this is to actually measure the acceleration of the universe directly. When I think of acceleration, I'm thinking of things are moving at a certain speed. I'll measure that speed. A little bit later, I'll measure it, and the speed should have increased. Nobody's done that experiment, and that's what we're trying to do. It's called a redshift drift experiment. And so the idea there is if we look at really distant objects in the universe, they're moving away at a certain velocity, we can measure that velocity really precisely. So to make that precision measurement, we actually have to have a huge collecting area of telescopes to gather up all the light that we need to make the precision measurements. And even then, once we have that, we have to make very precise measurements using technologies like laser frequency combs that we develop here at Creole at UCS. So for the big telescopes, what you can see over here behind us, that's not a big telescope, it's a very small telescope. So what we're trying to do is to take this sort of small telescopes, we robotize them, we automate them, and then we connect them all together. We connect their light output together through a technology here called a photonic lantern. That lets us link, say, 7 small telescopes into a single fiber optic output that we can then feed into our measurement equipment. And then you could take 7 of those, take those 7 fibers, combine them into one, and so on. So it scales up and makes a really big telescope collecting area, but makes it about 10 times cheaper than anybody else can make it right now. That's what our little army of robotic telescopes will do together, all looking at the same quasar, tracking it across the sky and sending all the light from that into a precision measurement device. We have a number of PhD students who are involved with this research working on it, and particularly the Polyoculus project is right now being led by Christina Moraitis, who is a PhD student right here at the University of Central Florida.
Since my first year of grad school, I've been sort of leading the Polyoculus prototype project, which we call the Original Polyoculus Array. And you can also say that as OPA, essentially a way to prove the concept that you can take several small telescopes, like the one you see in the background, and combine their light through photonic lanterns and optical fibers. I have built a lot of the prototype parts for OPA, for Polyoculus. I've also designed and built the spectrograph for OPA, which is a device that analyzes the light that the telescopes observe. But to be a part of something that's so big, questionably Nobel-worthy in the future, is always keeps you motivated to keep helping out and to keep working on even the small parts of the project and the small parts that, aren't as glamorous as making the final measurement that we're looking for.